A bit about column store indexes then, a particular type of index that I can use to work with my data. And in this case, we're back to our sales.product table. You can see I've got my product ID, my name, my price, and my supplier in that table. And I want to be able to query that, and I want to do it using really high performance. Perhaps this table is part of a data warehouse. So maybe this would be perhaps a dimension table that I would have in a data warehouse, and I'd have a fact table that had maybe the sales of the products or something like that. And what I want to do is I want to take my index, and rather than have my index organized like this in these sort of pages that contain rows, which is a traditional index would store it, I want to store it a slightly different way. I actually want to split those into row groups and index the columns. I actually want to be able to use the columns as the basis of the index. So we've got row groups that are then organized into these segments that are going to be the columns that allow me to store the indexes. And that's going to allow me to take advantage of things like compression, because a lot of these columns may have multiple rows that have the same value, and that makes them nice and easy to compress, and then we can store that in memory, and that's going to optimize my ability to query that. So we compress these segments, we put them in memory, and we're then able to query them using this column store idea. So it's a slightly different way of thinking about indexes. And what we're going to do is we're going to create this using a similar syntax to what we saw before, but this time it's create clustered column store index and then the name of the index on the table. Now you notice, because I'm creating a clustered column store index on a table, I haven't specified any individual columns, because I can create a column store index for the entire table. And it's just going to create an index that has all of those different columns, those segments stored in memory, and I can then query that using the column store index and get the benefits of performance. So that's a clustered column store index. I've also got the option of creating non-clustered column store indexes. So I can create a non-clustered column store index, and then I can specify the individual field names that I want to use in this case. So I've created that on the product ID and the name. Those might be the ones that I most commonly query, so I can go ahead and create that column store index on those. So column store indexes then, the important things to remember from the point of view of really just getting the fundamentals of this, they are stored in memory, and they store the data by column instead of by row. So traditional indexes, you're really indexing to find a row of data. Here we're indexing by column, and that allows us, when we've got columns that have multiple instances of the same value in that column, we get really good compression ratios that allows us to compress that data, compress the indexes, and store that in memory to improve performance. They can be clustered or non-clustered, and a clustered column store index can include all of the columns. I can just create a clustered column store index on the table, and that will by default include all of the columns in the table. And I can create only one clustered column store index per table. That's important to remember as well. When you create a table, just like an ordinary index, you can only have one clustered index. You can only have one clustered column store index per table.
Wow, column store indexes look kind of cool. Can we see some more?
Sure, let's have a look. Right, well, we're going to take a look at column store indexes. So again, I've got a couple of tables here. I've got one called dbo.product and one called dbo.product inventory. So I've got a table of products, and then the inventory table tells me information about how many of those products I have in stock and where they're stored in the warehouse. So if I have a look down here, I can see here's the product table. I've got a list of products with their names and numbers and all that sort of thing. And if I scroll down underneath that, I've got another table called product inventory, where I've got the product ID, so that's what we're relating the tables on, and then I've got various locations, shelves, bins, and quantities of where I'm storing that product in my warehouse. So again, we're going to turn our statistics IO on like we did in the previous demo, where we looked at just regular indexes, because I want to see what's happening when I go and query these two tables. And I'm going to stick on the actual execution plan here, just so we see what's happening under the covers. And we're ready to go and query these tables. Now this query, we haven't really looked at the syntax in any detail before, but we're selecting the name of the product from the product table and the list price, so the product name and the product list price. And then from the inventory table, we're bringing back the shelf, the bin, and the quantity. And we're bringing that from the product table, which we're just calling P, just for convenience, and joining that to the product inventory table, which we're calling I, and the join is based on that common key. Remember that foreign key relationship we talked about way back at the beginning, where we've got our product ID that relates to the product ID in the inventory table. And then we're filtering on the product name. So it's a bit more of a complicated query than we might have seen so far, but fundamentally we're just bringing back some data from both of these tables, and we're filtering based on the product name rear brakes. I'm only interested in that particular product, and what I want to know is bring back the name and the price of that product and the shelf, bin and quantity that I have in the warehouse. Let's go ahead and run that query. And I get it back and I can see, well, I've got 3 rows, so there's 3 locations where I store that product on shelf E, shelf M and shelf W, and I can see the bin and the quantity that I have in the warehouse there. So let's have a look at what happened when we ran that query. If I look at the execution plan, it basically did 2 table scans. Because these tables are heaps, there are no indexes on them. So we've scanned the products table, we've scanned the product inventory table, we've used a hash match to join those things together. Don't worry too much about the details of that, but we've joined them together and got back the results. And if I look at the messages, I can see for all of the different operations that happened there, the number of reads that happened. And I'm interested in the logical reads. So I've got my product was logical read 13, and my product inventory table, there were 7 logical reads that returned that data. So a fair amount of work going on under the covers to return the information. Let's create a column store index. I'm going to create a clustered column store index. And a clustered column store index is always based on all of the columns in the table. So we're going to create that on the product inventory table. So clustered column store index. And now let's go and run that same query again. So here we are. We're going to bring back all of the locations in my warehouse for my rear brakes. And we get back the same results. And this time if I look at the execution plan, we've actually, when it came to taking the data from the products table, we still don't have any indexes on the products table, so we just scanned that table. And that was 71% of the cost of the query. So 71% effectively of the effort was involved in scanning that table. And then we've used this column store index that we created on our product inventory table to bring back the data from that table. And if I look at the messages tab here, well, there are fewer operations. There's only 3 operations going on here. And what we've done here is we've still got logical reads going on from my product inventory table. There are actually none because it didn't need to get them. It got them from the from the product inventory table. There are no logical reads. It got some logical reads from the product table, but it read a segment from the product inventory table. So when we have a column store index, we're actually storing the data column-wise in segments. So it only read 1 segment from there, and it was able to get that data. Well, let's see if we can further optimize this by adding another column store index. This time we'll add a non-clustered column store index on the product table. And because it's a non-clustered index, we can specify individual columns. So we're going to have a product ID, name, and list price columns in this index. Let's go ahead and create that. And again, we'll go and run that same query again just to see what actually happens under the covers. Get back the same results as you would expect. And the execution plan this time, it uses both of my column store indexes. It uses the clustered column store index on the product inventory table, and it uses the non-clustered column store index on the product table to bring back the data. And again, when I look at the operations here, I'm getting segment counts here because it's reading those segments from the in-memory column store index, and that's going to optimize the query and make that perform faster. We don't really notice it, particularly in this example because it's such a small table, but with a very large table that you might have in something like a data warehouse where you've got potentially millions of rows, then this type of operation can really improve the performance of your queries. All right, well, I've already created a database here. I've created a database called memdb, and that's because if I'm going to use memory optimized tables, there is something I have to do when I create the database. I have to create this thing called a file group that contains memory optimized data. So don't worry about the details of that too much. It's just something we have to do when we're going to be using this technology. We have to add this type of file group to the database. But I've already done that, and I'm now ready to go and create a memory optimized table. So way back at the beginning of this course, we looked at creating tables using the create table statement, and that's exactly what we're going to do. We're going to use this memdb database. We're going to create a table called dbo.memory table. It's going to have an ID column which is of type integer, which is the primary key. And because it's an in-memory table, I've got this option of using what's called a non-clustered hash, where I basically just hash the value into in-memory buckets. So I'm storing it in locations in memory based on the value that's in that column. So I'm storing that data in memory. And I'm going to have a date value, which is just a date time, and that's going to allow null values. So we're creating a date time, a column called date value, which stores date time values. Now the important bit here is in this with clause I've said with memory optimized equals on. So it's an in-memory table that I'm creating. And the durability is I'm going to persist the schema and the data to disk. So as well as having the data in memory, it's going to be persisted so that when the database is taken down and then brought back up again, the table still exists. Sometimes you might just want to store the schema. You might want to let the data get deleted every time the database is taken off, maybe just because you're using it as some sort of cache for a web application or something like that. But we're going to go ahead and create that table. Let's go and do that. And just for comparison, I'm going to create the same table, the same structure, but just as a regular on-disk table, the same type of table we've been using all the way through. So we're just going to get a table called disk table, which has an integer ID column and a date value column. So exactly the same structure. Let's go ahead and create that. And what I'm going to do is I'm going to use a transaction. We talked about transactions earlier. We're going to use a transaction and we're going to insert 500,000 rows into the disk table. And while that's running, I'm also going to insert 500,000 rows into the in-memory table. So I'm using pretty much exactly the same code except for the name of the table. So I'm just going to copy the code for the memory table to the clipboard. And I'm going to go and run this code that inserts 500,000 rows into the disk table. So let's go and run that. And off that goes and starts running. I can see it's executing query, and I can see down here the amount of time that's elapsing as that goes along. So we're at 6 seconds now. And while that's running, I'm just going to create a new query. And I'm going to paste in the same code and insert into the in-memory table. So we'll run that at the same time, simultaneously. We're running both of these queries. So this one starts executing, and I can see the amount of time elapsed down here. And that one's now finished. So that took 7 seconds. And if I go back to this one, well, that's finished as well, but it took 17 seconds. So I can already see, because my memory table is in memory, using a transaction to insert 500,000 rows was quicker. It was 10 seconds quicker doing that in the in-memory table than on the disk table. And just to verify that we have in fact done that, if I select the count of rows from the disk table, there's 500,000. And if I select the count of rows from the memory table, there's also 500,000. So no cheating, we've got nothing up my sleeves. We're just genuinely seeing that it's faster to insert data into an in-memory table. Now if I go and delete from the disk table, let's go ahead and do that. We'll delete from there. Off it goes, and it starts deleting. It's taking a little bit of time. Again, we'll just do the same thing in another connection from the memory table. So we'll just go and delete from there. And that happens almost instantaneously. It was 0 seconds on the clock for deleting from the in-memory table, whereas it took 14 seconds to delete those rows from the disk table. So again, the delete is another thing that's taking longer to do on the disk-based table. Now, one of the things we talked about when we were talking about this earlier on was we looked at the idea of native stored procedures. So as well as creating these in-memory tables that are actually C# structs that are then compiled to DLLs, we can create stored procedures that are C# code compiled to DLL. And I'm going to create one called insert data. And the way that we make it a native compiled stored procedure is we say with native compilation. So native compilation, another couple of options on here we don't need to worry too much about. And it's going to use this atomic transaction. It begins a transaction, and it's going to do the same thing we did earlier on. It's going to loop around. It's going to insert 500,000 rows into that table. So we'll go ahead and create that stored procedure. So I now have a natively compiled stored procedure that's an in-memory DLL and a natively or a memory optimized table that again is an in-memory DLL. So let's run that stored procedure, which does exactly the same insert we did earlier on. And you might remember it took 17 seconds to insert 500,000 rows into the disk-based table. It took 7 seconds to insert 500,000 rows into the memory table. If I use a memory optimized stored procedure, well, it took less than a second to insert 500,000 rows. So again, we're seeing that in-memory technology for both tables and stored procedures, in this particular case, because it's a latch-bound workload, there's a transaction going on that's locking pages, it's significantly faster using this in-memory technology to work with these tables. All right, so we've covered a few things in this module to optimize performance. Let's just recap on what we've looked at. So we talked about using indexes to optimize select performance, and you can have one clustered index on each table and multiple non-clustered indexes per table. It does optimize the select performance. You do have to be careful that, if you have just index everything, then your inserts and updates are all going to suffer performance issues, but it's a good way of optimizing select performance. We talked about column store indexes. Those work really well in those kind of large-scale data warehousing type scenarios. And what we're doing there is effectively indexing based on columns rather than rows, and we're storing those column indexes in memory. So we're getting some good performance optimization from that. Works very well when you've got highly compressible data, columns that have the same repeated value in them.
And we saw that there were some improvements in SQL 2016 for this.
Yeah. And we've also talked about memory optimized tables. So the idea of creating a table, but actually when we create it, under the covers, SQL Server generates a C# struct that represents that table, compiles that into a DLL and stores that in memory. So we get that in-memory performance. And we can do the same thing with stored procedures. We natively compile stored procedures. The big scenario where you want to use that is where you have contention-bound workloads, where you've got multiple people trying to access the same data at the same time. If you're using transactions to lock the tables, then that can give you contention issues. In-memory tables are a great way of optimizing that particular workload. So hopefully you've enjoyed looking at ways of optimizing the database. Join us in the next module as we move on through the course.
Welcome back. In this module, Graham and I are going to talk about non-relational data types. We'll talk about XML, we'll talk about JSON, we'll talk about using a document database, and we'll even talk a little bit about spatial data for maps. All right, well, to talk about XML in SQL Server has a little bit of prerequisite knowledge needed. And this course isn't designed to get into any real depth about XML, but help you understand where XML fits in the overall scheme of things with SQL Server. So let's start with a very quick primer on what XML is about. And so you'll see a blob of XML on my screen. And if you've never worked with XML before, it may look like, boy, there's a lot of stuff there. If you've worked with XML, you'll probably recognize quite a few things. So again, without going in tremendous depth, let's talk about what XML represents and why you might use it. So why work with XML data in SQL Server or in Azure SQL Database? Well, basically, it's because you already have XML, and you need to store it. You need to be able to transmit it between applications. You're typically not going to be creating new applications using a SQL database and then decide to use XML as the data type. Typically, you're using XML because you're already interchanging with other applications. So let's take a quick look at what makes this XML. The first thing you might notice as you're looking at the code is that everything's wrapped in angle brackets, and if you've worked with other markup languages like HTML, for example, this might look familiar. Let's take a look at some of the things that make this up. So we start with a processing instruction. That first line that begins and ends with question marks is essentially an instruction to the parser that's built into whatever application is working with the XML. So SQL Server and Azure SQL Database have a built-in XML parser, as does a web browser, for example. So that's a processing instruction that just happens to say things like what version of XML am I, what kind of character encoding am I using. It's not stuff that we're going to care about much, except that your parser will want it there. And then you'll start to see the actual payload of the XML in the form of elements. And so the interesting thing about XML is that unlike HTML, the elements are user-defined, or in this case, developer-defined. That's us. So we're defining an element called salesperson, for example. And here we've got a salesperson, and there's an ID value and a name value, and those are actually going to be called attributes. Again, these are things that we define, and the beauty about working with this in SQL Server is that SQL Server can recognize them, and SQL Server can store them and operate on them. So we've got elements such as the salesperson, and we're storing attributes like their ID and their name. We'll see the ability to store those attributes either as quote delimited or simply as text. And the difference between these basically goes to what kind of programmatic operations you'll perform to extract or modify those. You'll see, again, more interesting things with collections of attributes. I've got a collection here called items, and it's got two different item attributes, which then, item elements, which then have attributes. And there's no sort order about this yet. The only real rules are that the brackets have to match and that it is case sensitive. So how do I work with this with SQL Server? Let's take some sample data. I've got a portion of a table. In this case, I'm going to use a sample table called saleslt.customer. And I'm going to pull the last name out of it, but I'm going to use the top operator here simply to prevent pulling hundreds and thousands of records out of the column. So I'm going to say select top 5 last name from saleslt.customer. And if I ran that all by itself, I'd get results similar to what you see on the right-hand side of my screen. But if I add some of SQL Server's XML processing instructions, I can get that converted to XML without having to write a whole lot of additional code. So in this particular case, I'm saying I want these results as XML using an auto formatting rule, and I'm going to wrap these in a root element called customer. So if you recall from the previous slide, we had a sales order, and now we've got one called customer. So if I execute this in SQL Server, I'll get a result back similar to what you see. So it says, all right, well, for each of these customers, we're going to give it an element name of sales.lt.customer. That's the table name. And what's doing this is that auto instruction. And then the column name of last name equals, and then we've got the attribute value, which is G or Harris or Carreras or what have you. So that's one way you can work with XML. And so you can have data that's not even in XML in SQL Server and retrieve it in that form. Now, I should point out there's a bit more to it than that as you get into the nuts and bolts of it. For example, SQL Server doesn't put that prologue. And there are some other bits to the XML that a very strict parser might object to. And so you might have to do some additional massaging. Some other things you can do with XML in SQL Server and Azure SQL Database are do things like passing in an entire blob of XML in a variable, for example, and then traversing the hierarchy in that XML to pull out information. So here we've got some code using the from open XML function where we're passing in a variable and then we're telling it what part of the tree to traverse. So start at the root level and move down to the customer level. And then take those results and assign them column names of customer ID and contact name. And so the results might look like this. So the idea here is you can have an application pass in a chunk of XML as text, and SQL Server will be able to interpret it and figure out what the hierarchy is, what's an element, what's a child element, what's an attribute, what's a value, and bring those back. I'll show you more of this later in the course. So how do we do this? What's available? There's a wide range of things for XML support in SQL Server. I won't read this slide to you, but you'll see some of the options. So there's an XML data type, for example, where we can actually store the XML in a native form. Instead of storing it as text and having to convert it to and fro, we can store it in an XML value. There's the XML, the XQuery feature that gives us that language that will enable us to walk down the nodes of the hierarchy. There are a whole set of index structures that we can build to improve performance, and so on.
So the XML stuff looks pretty useful. I think a lot of people have worked with XML and need to work with that. Let's see an example of that.
All right, we've got a demo. Let's take a look. Well, our next topic is JSON, and JSON is part of the larger NoSQL movement. And what some people think of when they think of NoSQL is that they don't want to have a SQL Server. They don't want to have a heavy-duty relational engine. And one of the things that's interesting about SQL Server support for what we're going to see is that you can actually think of NoSQL as not only SQL, which is to say you've got your relational data, but you can also have this non-relational data, such as XML that we just talked about, and then some of the other things we're going to look at here. So with that as context, let's talk about JSON. So what is JSON? JSON is the JavaScript object notation, and it's essentially a lightweight data interchange format. And you've thought, well, I've heard this before. That's what XML was called. I don't think anybody's ever called XML lightweight. But the idea here is it's easier to read and write, certainly, than XML. It's language independent, which means you can use any of your .NET languages or other languages to work with it. And if you're familiar with JavaScript, you're already familiar with the syntax for JSON because it uses objects and arrays and values just like you're used to with JavaScript. So the idea here is we can take JSON and store the application data natively in SQL Server instead of, again, passing in strings and having to convert them as we store them and convert them back as we read them out. Now, the way that we would store them in SQL Server is in using the nvarchar data type, or using another feature of the SQL Server data platform, which is called document DB, that we'll be looking at in the next topic. So at a very high level, again, our goal here is not so much to teach you all of the details of these, but to place them in context with the data family. Let's take a brief look at JSON objects. The idea is that we're going to identify name and value pairs using colons. So we're stripping away a lot of that extra language of XML with brackets and all of that, and we're simply going to have name colon value. If you're representing an object, you'll wrap that in curly braces. And if you've got multiple sets of name value pairs, you'll separate them by commas, as you see here on my screen. And what is also nice about this is that these objects can be nested. Let's see what that example that we looked at earlier of selecting last names from our customers table would look like if we're extracting this as JSON. So once again, we've got our last name column from saleslt.customer. Once again, I'm selecting only the top 5. And this time, instead of saying for XML auto, we're going to say for JSON auto, and we'll see that that's now being encoded. That's being passed out to us wrapped in square brackets, with then each record or row from the source table being wrapped in curly braces as a name value pair. So last name G, last name Harris, last name Carreras. And if you're reading this, you're thinking, well, gee, that's a little bit redundant, just like it was in XML. But the idea is that each value stands alone. We can tell what it is while we're looking at it. What's Gates? Gates is a last name. So with JSON, just like we could with XML, we also have some programmatic ways to handle it. So I might declare an nvarchar variable to put JSON data is. And when I do that, I'm going to create a schema using my key and value and type. But I don't necessarily have to strongly type these the way that I would XML or even T-SQL data. This can be assigned when I actually populate it. So I might declare this variable and then use the OpenJSON function to pull whatever values are out of that. So I might have values of nulls or strings or numbers. I can also store booleans. So the idea here is that if you're already using JSON in an application, or you want to use JSON in your application, you can take advantage of SQL Server and Azure SQL Database to store these.
All right, well, let's take a look at working with JSON then.
Sounds good. Here's a demo. So to talk about document DB, we need to talk a little bit about what it means to be a document, and then what kind of DB we're going to use, and why we bother. I mean, we just finished talking about JSON, where we knew we could talk about the key value pairs and just store them as strings. But let's dive into this a little bit more deeply. So first off, let's note that when we talk about a document in the context of document DB, we are not talking about Word or a Word document or an Excel spreadsheet or a PDF. What we're talking about instead is a JSON document. In other words, a collection of those key value pairs that we talked about in the previous section. And in the absence of something like a document DB, remember, there's no schema, there's no implied structure. You come as you are here, and if you're storing it in something like SQL Server in an nvarchar column, then you're just storing text, and it's up to the application to interpret. And that's fine, but we can go a little bit further when it comes to storage and when it comes to things like availability and that sort of thing. And that's where document DB comes into play. Right? We want to have a repository for this, and we don't necessarily want to have to roll our own and take responsibility for a number of the administrative and the maintenance sides of things. So first, let's differentiate between your classic SQL in a normalized database and then what we're talking about here with document DB. So as I move from left to right on my slide here, we're talking about a client application sending or receiving information about, say, a car. And in the case of working with classic SQL Server, classic relational data, we have to have a way of mapping the objects that we're representing in our code to the storage in the database, and that's the process of normalization. We pretty much pull that car apart into a million pieces, and we store them in all the parts that are similar, are stored in similar tables or what have you. Now, with something like document DB and this whole NoSQL movement, we have the ability to store it just the way we want, and that's sort of my bottom right here with come as you are. So how do we store this? What can we use? And that's where Azure Document DB comes into play. I won't read this slide to you, but I want to call out a couple of key points, and then I'll show you a little bit more in the demonstration. The primary thing from the perspective of the database developer is that this is a fully managed system. You send and receive JSON, and the Document DB service takes care of it. You query over JSON. You don't need to